So this is the third part of the physical techniques unit. We're going to look at resonance techniques and most especially nuclear magnetic resonance. So this technique allows the analysis of compounds that contain elements with magnetic nuclei, most especially hydrogen. The technique gives information on molecular structure, including the chemical environment, connectivity, and internuclear separations. The sample is placed in a magnetic field. The sample must have a nucleus that has a non-zero spin value. In other words, I must be greater than 0. And this technique is non-destructive, which means that we can get our sample back. Now, on the right-hand side, you will see a table which shows the spin characteristics of some common nuclei. Okay, I don't expect you to remember all of this. If required, I will give you this information. But you can see that the common elements that we analyze for or spectra that we carry out will be Proton Nmr, we do carbon-13 NMR, and anywhere where the spin is a fraction. We can do where the spin is greater than 0, but for example, the most common ones are Proton Nmr and carbon-13, and you can also see the natural abundance of these elements. So a nucleus of spin I can take up 2 times I plus 1 orientations relative to the direction of the applied magnetic field. So these orientations are going to have different energies, and hence there are 2 different energy levels of a nucleus are separated when the I is equal to 1/2. So for example, Proton Nmr, carbon-13 and 31 phosphorus. And we get something that looks like this on the right-hand side that indicates the separation of the nuclear energy levels. Just like we had atomic energy levels and molecular orbitals, so the nucleus can also have different energy levels. On this slide, we see what a NMR spectrometer looks like. So we have this huge superconducting magnet that has a probe that's inside. So we insert the sample into the probe and we let it do its thing, and out comes what looks like an NMR spectrum. And it's then our job to be able to interpret this spectrum. So the frequency of the NMR transition is going to depend on the local magnetic field experienced by the nucleus. This is called the chemical shift, and it is given the symbol delta. The chemical shift is the difference between the resonance frequency of the nuclei in the sample and that of a reference material. And it is given by the equation that you see at the bottom left of the slide over here. Okay, so you can see in this instance on the right-hand side in this diagram, the chemical shift increases going towards the left, and you can see that there's a shift between this peak and this peak of 100 Hertz. A nucleus can be shielded where the delta is less than 0, or deshielded where the delta is greater than 0. Okay, so we sometimes use TMS, which is tetramethylsilane, and we get one very strong peak, but then if we expand that peak, you can see that these peaks here are shielded, these ones here are deshielded. Even if we're seeing a peak that's roughly at 0 delta, there is splitting involved, and where we see chemical shift and we see how the nucleus can behave. On the right-hand side, this is a Proton Nmr spectrum where we use the TMS as a reference, and you can see that all the protons are deshielded, so they have a value larger than 0, and they are color coded so that you can see that the blue peak over here corresponds to the protons here and here. Okay, then we have the pink peak over here, which corresponds to this proton here. The red peak over here corresponds to these protons here. And then finally, way downfield, we call this downfield, we have this orange peak here, which corresponds to the proton attached to the hydroxy group. And this is how we characterize NMR spectra. We often have spin-spin coupling when we have more than one atom, and this results in what we call multiplets in the spectrum due to interactions between the two nuclei that are spinning in the magnetic field. We get a spin-spin coupling constant, which is called J, and if there are chemically equivalent nuclei, we don't get any spin-spin coupling. What we do get and sometimes see is a multiplet of 2I plus 1 lines when nucleus couples to a nucleus of spin I. So let's have a look at what's happening at the diagram on the right hand side here. Okay, we have this trifluorochloride molecule, trifluorochlorine, and we've got 2 fluorines in the axial position and 1 fluorine in the equatorial position. Now you will see that these 3 peaks here are what we call spin coupled. Okay, so that means that this fluorine can see this fluorine here and this fluorine here, and will result in 3 peaks, as you can see, peak 1, 2, and 3. Okay, and then the axial peaks can see this axial fluorine here can see this fluorine here, and then this axial peak fluorine here can see this fluorine here, but both of those are equivalent, so therefore we get what's called a doublet, and we can see there's these 2 peaks and they are equivalent. Okay, so that is what we see when we see spin-spin coupling. Now the time scale of an NMR is relatively slow, so spectra can be collected at different temperatures to change the peak resolution. Sometimes what happens is that it's very difficult to resolve peaks. So you'll see that in the diagram at the bottom, if we look over here at the red spectrum, you see that we've got 2 very broad peaks at the room temperature scale, which indicates that we are losing information down the bottom here. So what we do is we change the temperature to a much lower temperature. So instead of collecting at room temperature, now we take the spectrum at minus 80 degrees C, and now suddenly you see that we've got way better resolved peaks, and of course much more information comes out. Okay, so the changing the temperature then allows interconversion to become slow enough for separate resonances to be recorded and observed, and this phenomenon is called fluctionality. So sometimes it's very helpful to change the temperature so that we get extra information and we're able to resolve peaks as we need them. Now we can do solid state NMR. Remember that actually usually NMR is performed on compounds that are dissolved in solution. So we'll take the material and we'll dissolve it in an appropriate NMR solvent that will not interfere with the spectrum of the samples. So typical solvents that we use for proton NMR are deuterium oxide and deuterated chloroform. So the D stands for deuterium. With solid state NMR, we collect the NMR spectrum of the solid material without any influence of a solvent. As a result, we don't get great resolution because we aren't able to manipulate the NMR spectrum enough for us to get information. So high resolution of solid state NMR is not always obtained due to anisotropic interactions. Now, what are these things? These are dipolar magnetic couplings between the nuclei. Because we're in the solid state, the nuclei are much closer together to one another, And then we have this anisotropy, where we get very broad peaks. So we have to average out this anisotropy, and this can be done by spinning the sample at exceptionally high speeds at what we call a magic angle. Now the magic angle is 54.7 degrees. So this is a special technique called magic angle spinning NMR. And as an example that I show you on the slide, in the picture on the right hand side, we have a look at 29 silicon magic angle spinning NMR spectrum, where each resonance shows a different silicon environment, which means that the spectrum is very well resolved. So in this case, this picture here is of a zeolite material. So we've got these silicates that are bonded to aluminiums, and that's why we see that we've got Al groups here, and you can see that we've got 5 different peaks, well resolved to the baseline, indicating that we are able to determine the different environments of the silicons attached to the aluminium backbones at each of these points through the oxygen atoms. And finally, this slide just shows you the proton chemical shift ranges for various functional groups. So where can we look on the chemical shift scale relative to TMS, because we say that the tetramethylsilane is placed at delta equal to 0. So samples are recorded in deuterated chloroform, and we're able to then see where amide groups are, ester groups are, alcohols, ethers, sulfides, saturated alkanes, etc., etc., using this chart. So if we wanted to interpret an NMR spectrum, it becomes very useful for us to remember this so that we know roughly where things are when we get an NMR spectrum.